Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 1 of 2 on the topic of multiple linear regression, and we'll discuss extending the simple linear model. Let's get started. In the next 2 videos, we will build on concepts in exploratory data analysis, multivariate analysis, and simple linear regression to build multiple linear regression models. When explaining the variability in some observations, sometimes one explanatory variable is not enough. Making predictions about that variable may be possible when adding additional variables to the equation. Alternatively, the response variable may not be linear in the predictor variable, and you may need to use a higher order polynomial to explain the variability. You might think of the predictor variable as one variable, the predictor squared is another, the predictor cubed is a third, and so on. Most of these visualizations we will see will involve 2 predictor variables, since these representations are possible in 3 dimensions. However, there's no real limit to the number of predictors a model can have. However, there are practical limits. With 2 predictors, the problem is in 3 dimensions. The resulting predictions are made using a plane, which is defined by its slope between the response variable and predictor 1, and a second slope between the response variable and predictor 2. The errors, or residuals, are still the same, the difference between the real response variable value and the predicted value. However, instead of this being the point distance to a line, it's now to a plane. For higher dimensions, the geometry is more complex but has the same principle. Recall the simple linear regression equation. The 2 beta terms are the intercept and slope, and the epsilon term is the random error. The best fit line is the line with a beta naught and beta 1 that minimize the overall error between the line and the data used to fit it. When we expand the model to include more variables, each of the terms is now multivariate. All of the terms in bold are multivariate, that is, either vectors or matrices. Y, beta, and epsilon are n-length vectors, where n is the number of data in the model, and x is a k+1 by n matrix, where k is the number of predictor variables in the model. Each of the individual epsilons in the epsilon vector are mean zero normal variates with a common variance sigma squared. This hasn't changed from the simple linear model. The y vector is the value of the response variable at each of the n points. The x matrix starts with a column of 1s. These are here so that the intercept can be estimated. The intercept is lumped into the beta vector with the coefficient for all of the predictor variables. Since it's a constant for the model and doesn't vary by point, we have to indicate that it's a constant, and that's done with this column of 1s. Then, there's a column for each of the k predictor variables, with each column essentially being a vector containing the values of that predictor variable at each of the n points. The result is a matrix with n rows and k+1 columns, because the first column of constant values is added in for the intercept term. The beta vector has length k+1, with 1 entry for each predictor plus an extra 1, beta naught, for the intercept term. Finally, the epsilon vector contains the residual for each point. This notation will still work for simple linear regression and only 1 predictor. The x matrix would have 2 columns, and the beta vector would have a length of 2. Least squares estimation is still the tool we're going to turn to in order to find our model parameters. We want to find the values in vector beta that minimize the sum of squared errors just as before. I'll spare you the math, but the payoff is this solution. Note that it has the condition that the x transpose x product has to be invertible. If it's not invertible, another means for solving this equation must be used. This matrix product being not invertible can happen when 2 columns of x are linear combinations of other columns. For example, if 2 columns measure the same predictor variable except in different units. In those situations, instead of turning to a more complicated solving method, it's better to simply remove the redundant predictors from the model. When we go to perform these analyses ourselves, luckily we're not dealing with matrix math. Tools like Microsoft Excel's data analysis add-in make regression analysis pretty straightforward. The regression input is the same as it was in the simple regression case, but now for the input x, you specify multiple columns. The columns must be continuous, so you may need to rearrange your data to make it work. In this example, the 3 columns of data for precipitation, mean temperature, and mean dew point are being used. The precipitation and mean temperature predictors are being used to build a model predicting mean dew point. The regression output looks the same as the simple linear regression case with one notable difference: the extra row in the coefficients table. Here we can see that the data for both the precipitation and the mean temperature predictor are included, and each has their own coefficient and p-value. This is the same data and model except now in R. Notice in the model call at the top, all we had to do was include another predictor by adding it into the model formula with a plus sign. The model output looks much the same as the simple regression case, except just as it was in Excel, it has an extra row in the coefficients table. The output has the same look and feel for multiple regression as it does in the simple regression case. In the output, we're still mostly concerned with the same values that summarize the performance of the model. The biggest points of emphasis for a multiple regression model are the adjusted R-squared, the p-value for each predictor coefficient, and the model F-statistic p-value. The adjusted R-squared, listed on the second to last line of the summary, is a metric that summarizes model goodness of fit, but also penalizes the goodness of fit metric for adding extra model complexity. This comes in handy when you're considering different predictor variables and you want to know if adding a predictor to your model is worth the extra complexity. Every time you add a predictor, the multiple R-squared will go up or at least not decrease. However, for adjusted R-squared, each additional predictor is penalized, and if the increase in goodness of fit for the model with the new parameter doesn't overcome the additional complexity, adjusted R-squared will go down. For multiple regression models, I pay the most attention to the adjusted R-squared values when summarizing performance. Second, you will want to check the coefficient p-value for each predictor variable. When you add predictors to your model, you want to make sure the coefficient is significantly different than 0, which is indicated by a small p-value, usually less than 0.05. In most cases, you want all your predictors to be significant, but there are circumstances where the inclusion of a predictor makes the model better without the predictor having a small p-value. This brings us to the last statistic. The model F-statistic p-value indicates the strength of evidence that the model is better than one that has an intercept only, in other words, has no predictors. If the value is very small, then the model is better than the intercept only case. For multiple regression models, this statistic is important because it helps roll up the significance of the total model even if some of the predictors have weaker evidence for their significance. There are circumstances where a predictor added to the model will not be significant itself, but the adjusted R-squared goes up and the F-statistic p-value indicates that the model is better than an intercept-only model. In this case, I might be inclined to keep that additional parameter in the model even though it isn't significant, especially if I have a physical explanation for why that predictor should be included. The assumptions made in simple linear regression still hold for the multiple regression case and should be checked in the same way. You can check the linearity assumption using a fitted values versus residual plot. Constant variance can be checked using a scale location plot. Normal QQ plots can be used to check residual normality, and lag plots can be used to check residual independence. In this video, we discussed extending the simple linear model. 2 key points to take away from this video are: multiple linear regression is a generalization of simple linear regression, and all of the same assumptions made in simple linear regression still hold for multiple linear regression, and they need to be checked. Thanks, and tune into the next video in this series on multiple linear regression to learn about additional considerations for multiple linear regression models.